Hi everyone and welcome back to another lecture of computer organization and architecture. So today we'll start with the lecture 4A of this particular subject. So today we'll learn about data part. Basically how exactly an instruction is being fetched and what happens throughout the whole bus, how data gets transferred, those things I learned. So I gave you a high level picture previously. Now we'll exactly go into the CPU, inside the CPU, and see exactly how it decodes the instruction as well. We'll learn about decoding, we'll learn about control unit. So control unit is the main manager basically, which manages everything. Okay, so it is there to decode the instruction, what does each instruction means, and it instructs everything, right? So inside CPU we have control unit and arithmetic logic unit. Arithmetic logic unit performs the arithmetic and logical operations that will be given by the control unit. So that we'll learn. So I previously told you, right, later on we'll study about control unit. So today is the day we'll study about control unit. Then I will understand CPU cycle. So inside a CPU cycle, how much time happens. So we already know about instruction cycle. We'll know about what is CPU cycle, what is the difference between instruction cycle and CPU cycle. Then we'll learn about hardwired control unit. So there are many types of way in which you can implement your control unit. So one method is hardwired control unit. So and in the next lecture we'll learn different methods of control unit. So that we'll study in the next lecture. So yeah, what is basically I told you previously, CPU. What is a CPU? CPU is the brain of the computer responsible for processing input, managing data, producing output. It performs all essential operations required for the computer to function. This we already know. This I've already told you. It is basically the heart and brain of the CPU. Heart and brain. So without your heart and brain, your body will not work. Okay. Obviously, all the parts are responsible, but the most important parts are heart and brain. Okay, now you can think the brain to be the control unit and your heart to be the like also without heart also you cannot work, is the ALU. Why brain to be the control unit? Because control unit actually instructs everything what to perform. Heart does, heart just pumps the blood, right? Because brain is sending signal, pump the blood faster, so to pump the blood faster. So that is what control unit is. Control unit is the brain of the computer and heart is the ALU of the computer. Just giving you an analogy. It is nothing theoretical, nothing like that. I'm just giving you an analogy. So in this, what does data path mean? What do we mean by data path? Data path is a collection of hardware components within the CPU that perform operations on data. It includes functional units like ALU, multiplexer, and registers. Once I will show you the picture, there you will understand this. So data path, okay, the picture is not here. The picture is here, right? This is the data path. So what does data path means? Exactly what the name says, data and path. So it talks about how data flows. Now you need to focus more. How exactly, I will write in different color, exactly how the data flows through the whole CPU, right? Within the CPU, how is data flowing? So that is what it is saying. It is the interconnection of hardware components, right? Because you will obviously require hardware, right? Digital component is there which understands whether it is 0 and 1, but at the end it is a hardware component, right? So hardware, how is everything connected? So actually, I will tell you one thing, that everything is interconnected with respect to the control unit. So all the internal components, first thing is all the internal components of CPU are interconnected. Okay, if I can through what? Through control unit. Through control unit. Now, why is it so? Let's take an example of like your job or something. You are in the job, right? And your manager is there. So your manager is not just your manager. Your manager is manager of a lot of employees, right? Why is it so? Why is it so? Your manager needs to be in connect. So your manager is here. It needs to be in connect with lot of people. Why is it so? Because it needs to give assign task to everyone, because control unit is the main thing that assigns the task, and then control unit assigns the task, as I explained at the starting of this lecture. So obviously it has to be connected with all the components so that it can assign some task, right? Whether to perform a read or write. How it will assign that I will talk about later on, but for now control unit at least needs to be connected. This is hardware, I'm talking about hardware. It needs to be connected to every component of the CPU to assign any task to any of the component. Let's say ALU, it needs to be connected to ALU, it needs to be connected to the PC, it needs to be connected to the instruction register, it needs to be connected to everything. So if you see in the block diagram, this bus, right, there is a common interconnection between everything, not just control unit, through everything. Why is that the case? Because where is my control unit? So like control, yeah, this is my control unit, the instruction decoder and control signal. So it through the bus it will send some control signal to PC. So generally PC can have two inputs through the control signal. It can either give data on the bus or it can take data from the bus. Because sometimes what I want to perform is I want to perform write operation on PC. So it will be in, then the in control signal will be 1. If I want to read from the PC, then the out control signal will be 1. Okay. So exactly, I hope you understood that how does my instructional logic decoder send control signals. How does it decode? We'll come to that later on. First of all, let's just understand that control unit has decoded the instruction, and it knows that I have to read from the PC. If it has to read from the PC, it will send some signal through this common bus, to the PC that, hey man, I have made my signal 1 out of the signal 1, so please give my value, give my PC value. So that is what my control unit does. Okay. So there are many components of a control unit. That is ALU. Obviously ALU, it's not control unit, sorry, data path. ALU will be there. Performs arithmetic and logical units, multipliers and dividers. Handles complex arithmetic computation. Okay. So this is just the extension of ALU. Registers, temporary storage for data. So there are many registers here, right? Like memory data register, instruction register, and these general purpose register. So in the data path, all these components will be present. That is what is written. What components are present in the data path? Obviously buses will be there to transfer the data. And control signals directs the flow of the data and determine operation to perform. So what type of operation do I need to perform? Do I need to perform read operation, write operation? Your manager tells you, right, what you need to do. Okay, like exactly what task you need to accomplish, that your manager tells you. So then let's come to the function of a data path. Instruction fetch. So I will tell you the whole cycle. Instruction cycle I have already explained. Again I will explain with the help of data path now. So things will be more and more clear now. So there are two cycles, right? One is execute cycle and instruction fetch. So what happens in instruction fetch? There are a lot of things that happen on instruction fetch only. In instruction fetch, retrieves instructions from memory. It retrieves the instructions from the memory. Okay. So from the memory somewhere there will be some instruction present, right? In the memory somewhere there will be some instruction present. I will retrieve it and store it where? I'll store it in instruction register. So instruction register gets the instruction from the memory at the program's counter's value. So PC will point to memory and I will store it in my instruction register that I already have told. I will show with the data path example. Then what happens? Data movement transfers data between registers and memory execution. Like then some data movement happens like operand fetch. After instruction fetch, what we do? Operand fetch was also inside the cycle, right? Inside the execution cycle. So we can do operand fetch, or we can fetch the address of the operands. Then again I will go to the effective address. Then what happens? Execution. It processes data using the ALU. So the data has been fetched to its own registers. Then we process the data using ALU, and the control signal directs it, and other functional units. There are other functional units nowadays. Obviously ALU is not there, right? A lot of things are there that does the computations. So how does it happen actually in the data path? How does it happen? I've already told you CU is your manager. Okay. So first what will happen is point 1. If let's understand, if I am loading something, okay, I am doing some instruction. I have an instruction I1 that is present at this location 2000. Okay, so hence my PC value will be what? PC value will be simply 2000. PC value is 2000, right? PC value initially is 2000. So when I will start to like execute this instruction, what will happen? First I will fetch this instruction. So first the instruction will be first the address of the first the contents of the PC will be copied to memory address register. So it's not like I will directly copy the instruction register. It's not like that. It's not that simple. So first I will copy the contents present in PC to memory address register. So what will happen? Exactly what will happen? In step 1, CU will make the out of PC to be 1 and in of memory address register to be 1. All the other bits will be 0. Okay, so what will happen? Data will go out from the PC on the common system bus and it will go to where? It will go to memory address bus, as in is on for memory address register and out is on for PC. So data will go from here to memory address register. This is the data path. Okay, next what will happen? Now the address has been stored in memory address register. Then I will go to that location that is pointed by memory address register and I will copy that on my instruction register. So now what will happen is that then I will go to the memory address register that is stored in MAR and store the contents in IR. So somewhere in memory it will be stored, right? Like 2000. MAR has 2000 now. So what will happen is now the control signal will actually make the MAR out. Okay, MAR out, and then it will go to the MAR signal. Here what will happen? CU will make the CU makes the out of MAR 1 and in of IR as 1. Whenever there is some out signal, right, we already know that it is coming from an address register. So we will only go to the address. We will not directly store it somewhere. We will directly go to that address. Whatever the output of MAR, it is already known to me that it is an address. It is address of what? It can be address of anything like operand, or it can be address of a a instruction. Okay, so it will be address and I will go to that address somewhere in the memory location. Somewhere in the memory there will be some instruction, and that instruction will be like this instruction will be fetched, copied to IR, as IR has its in signal on. Okay, so it will be copied to IR. So now it is done. So after this what will happen? Then the control unit will take some input from the IR. So after this the control unit, so instruction has been fetched. So as soon as the instruction has been fetched, what will the control unit say? Control unit will then tell, please PC update your value PC +1. Then what will happen? Then I will go, then the third step will happen. Then here, this is the decoding step, right? Decoding step. Here control unit takes input from the IR and it decodes. We have a decoding circuit. Don't worry about that. We have a decoding circuit. I will talk about that later on. It will decode, right? It will simply decode the instruction. So if there is some like data storage, something like that, right? What we do is we store it. Like if there is some data in or data out, like we want to fetch the operands. So here after decoding, what the control unit will do is it will do operand fetch. If there is some operand fetch or if there is some addressing mode, whatever there is, it depends. All of it depends on the instruction. So what will happen is now somehow control unit has got to know that there are two operands and the addresses of this operand has been provided. So operand 1 has address location as 2000, not 2100, and operand 2 has address location of 200. Okay, so these are the address locations of the operand 1 and operand 2. So now we know this. Now what we can do? Now what we can do is we will go to this address and fetch this where. Now I will store these addresses where these addresses will again be stored in memory address register, and then after storing it in memory address register, control unit will send some signals. Then again I will go to this location and then the operands will be stored in memory data register. Okay, why? Because CPU obviously, again I told you previously, it doesn't trust everyone. So there will be some memory data register where it will be stored. Then from the memory data register, the ALU will take inputs. Okay, ALU doesn't take inputs directly. From the memory data register, ALU will take some inputs. Okay, so this is just an example. Don't go too much into this. Just I'm giving you an example. So after that, the ALU will store back the results. ALU will write the results in accumulator. Result is stored. Okay, and after that result is stored, we then put it in the memory data register. From accumulator it goes to memory data register, and from there it goes to the memory. Okay, it doesn't directly go to the memory. We don't directly do it. We store it in memory data register, and then control unit gives some MDR, memory data register signal out to be 1, and then the data goes out and it goes into the memory. Okay, so this is what happens. Like I have just given you a high level example. A lot of things internally happen also, but I have just tried to give you a high level example exactly how data flows and what happens in a data path. So this is a data path basically. I hope you understood the significance of data path. Okay, so the main question comes is, why is a common bus used in a computer system? Why is there a common bus? What is the requirement for common bus? If a system has 32 registers, memory, an ALU and a program status word. So like I've just given you an example and other components. There would be minimum of 36 components. So just giving you an example. So here if I consider if a CPU has 32 registers, memory, an ALU, a program status word, it will have 36 components. Connecting this would require more than 1260 connections. How am I getting this 1260? Basically, I have total 36 components. 36 components I have, and I have to choose either two, because all those two should always be interconnected. I have to choose any two, and any two should be interconnected. How many ways can I choose two? Okay, it should be 36 C2, that is 1 2, that is 36 into 35, that is 1260. Let's take a smaller example. If I have two components and if I want to connect those two, how many ways can I connect it? In only single way, just a single way, right? It is 2C2 only, this 2. If I have three components, how many ways can I connect it? I have three components, how many ways can I connect it? So this is C1, this is C1, this is C2, and this is C3. Okay, so this will be here, this will be here, and this will be here, and all three are connected, so it is 3C2, correct? It will be 3C2. Why it will be 3C2? I have three components and always I have to choose any two, because this wire can be connected between any two. Then if I have four components, okay, I will take in the next page. I'll go in the next page. This is C1, this is C2, this is C3, this is C4. Now it is connected here, here it should be connected, here it should be connected, here. Okay, and this also should be connected, right? Any two components I have to choose, So how many ways? 1, 2, how many wires are there? 1, 2, 3, 4, 5, 6. Now if I apply my formula, 4 components, I have to choose any two, 4C2. It is 4 times 3 divided by 2. So it is simply 2 times 3, that is 6. Why this divide by 2 comes? Because this is the twice, like few connections will be repeated if I am choosing the repeated ones. So I hope you get the understanding of this. So yeah, this right, this should be actually divided by 2 as well. There will be division by 2. So there will be 1260 wires. Can you imagine how many wires is that? That is huge number of wires. To reduce the complexity, a common bus is introduced to connect all the components. So I cannot do like each component will be interconnected by them. Then like each when I will send some data from C1 to C3, only this wire will be used. If I send some data from C2 to C4, only this wire will be used. That will be very complex and hectic because I will have so many wires. I don't want that. So obviously, to simplify, we have a common bus, a common where data flows at once. Only two components can talk. In new architecture, things can be different, so don't come in the comment section and blame me, sir, you got it wrong. I am just giving you an example. Obviously, when we implement, things will change. I am giving you a simplistic view that at once only two components can talk. One will send the data, another one will receive the data on the common bus. Only two components communicate at a time. Control signal determines which components can access the bus. So I told you, right? Here I have told you that it makes CU makes MDR out 1, CU makes this out MAR 1, in IR 1, all these things it makes, right? So it should be MDR out MDR actually, not MDR. So CU actually decides which bus needs to be turned on. So just like your manager decides who needs to do what task, same like that. This approach simplifies and minimizes the required connections. Okay, so I'm just giving you an example. Then currently the architecture can be different. I'm just giving you how we started. Now, how ALU MBR registers common bus process the data. I've already explained this actually. You can go through this. You can read this, okay? You can go through this. I have told you, right? We have elementary operations known as hardware operations. So each time a elementary operation has been performed, it is known as a micro operation. Okay, a register to register transfer operation is a micro operation. So I have already explained this, like how data transfer works. So you can go through and read this. I will not read this again. Okay, so let's do a question. So try to pause the video and whatever concept you have learned till now, try to solve it by yourself. So let's read this question. Consider the following data path. Just hold on a second. Consider the following data path. The ALU, the bus and the registers in the data path are of identical size. So everything is of identical size, like all the registers are identical size. All operations including incrementation of PC and the GRPs are carried out by the ALU. So even if I increment my PC, right, PC incrementation, okay, after every instruction page, that will be correct done by ALU. That there is no separate ALU for that. 2 clock cycles are needed for memory read. Okay, the first one for loading the address in the MAR and the next one for loading data from MDR. So as I told you previously, right, we don't exactly load from the memory directly. First we load the address of the data on the MAR, then we load it to the MDR. So one cycle, 1 clock for MAR, loading the address to the MAR, then another clock for loading the data to the MDR. Okay, next what we have, next we have the instruction add R0 R0 has the register transfer interpretation that R0 will be equals to R0 plus R1. The minimum number of clock cycles needed for the execution of this instruction. So what will be the minimum number of clock cycles for this instruction? So they are only telling me execution cycle, right? Please read, don't mess up here. Execution cycle of the instruction. So I don't need to fetch the instruction. Again, they have mentioned here execution cycle, so we can ignore fetch cycle. Assumption is the instruction has already been fetched. The instruction has already been fetched in the IR. Okay, I don't need to do that. So how many clock cycles will I require? So first, one clock cycle will be required because R0, right? It is already inside the CPU. I don't need another memory access here. I directly go to R0 and get the data. So first one cycle for storing the value of R0 to some memory data register of CPU, MDR of CPU 1. Then another cycle, this is just for the data transfer. Address I don't need because this is inside the CPU, this is the CPU register. Another cycle for storing the data MDR2 from R1. Then I perform my addition, right? So it adds the value. To perform addition, do I need any extra cycle? They have just mentioned me that for reading and writing the data, I need one cycle. They have not told me that I will need any extra cycle for adding the data. I can instantly add the data and then store the result. So like I will get the data to S. Here they have given me the two inputs as S and T, right? So I will from this registers, the data will, one data will come to S, another data will come to T. So this is MDR1 and MDR2. I can write this as directly S and T. Okay. Next, I will add them and directly put it in the bus. It is there in the bus, right? So this, then it is in the bus. So it will go to where it will be stored in register. So again, I will require one more cycle to store the value, to transfer the value from ALU to the register. Correct. So one cycle will be taken to transfer the data from accumulator to register R0. So total how many cycles I required? 3 cycles. If fetch cycle was included, then how many cycles will be required? How many cycles will be required if fetch cycle was included? If fetch cycle was included, I have to first load the address on MAR from the PC. That will be one cycle. Then I have to load the instruction that is pointed by the MAR to IR. So 2 cycles. Okay. 2 cycles. So total how many cycles I will be requiring? For the whole instruction, 5 cycles. Total I will be requiring 5 cycles. Now there is an important word here. Important mention that all the data path have identical size. Why is it so important? Why is it so important to read this statement? All this path, right, has identical size. Let me take an example. Let's say your signal path or data path can only transfer 8 bits in one cycle, but your general purpose registers are 16 bits. So how many cycles will it require for me to transfer the data from a general purpose register to T? Will it be 1 or 2 cycles? Please let me know in the comments or just reply me somewhere. How many cycles will I be requiring to transfer the data from a general purpose register to T register? How many cycles? 2 cycles. There I'll be requiring 2 cycles. Okay. So why? In the cycle C1, first 8 bits will go, then in the second cycle, next 8 bits will go, total 16 bits. I cannot transfer all 8 bits at a time. So it will be twice as much. Now if I had been requiring 3 cycles, there I would have been requiring 6 cycles. And for the whole instruction, it will be 10 cycles. If everything is 16 bit data, if let's for example take that the PC value is 8 bits only. It is 8 bits only. So it will take now 6 cycles for this particular execution phase, and for the PC value it will take 3 cycles, because here, right, I will not be requiring 2 cycles, only 3 cycles. So total I will have 9 cycles. Total instruction cycle will be 9. So it depends, right? So you have to read all this statement, small information. Small informations are also very, very important. They can trick you in the examination. Let's read this next question. So consider the following data path. We have this common bus, MAR, MDR, all these things are there. These will go to the memory, and these are PCIR. All these things we know. Consider an instruction, same thing only. R0 is equals to R1 plus R2. The following steps are used to execute it over the given data path. Assume that the PC is incremented appropriately. So PC is incremented appropriately. We don't have to worry about the PC. So it is telling us we don't have to worry about the PC. We don't have to worry about increment of PC. The subscripts R and W are for read and write operation. So these are few operations that are happening, right? Which one of the following is the correct order of execution of the above steps? Which of the following is the correct order of execution of the above steps? So in a data path, what happens? I've already explained at the starting of the lecture exactly what is the sequence of steps that happens, right? In a data path, it is asking exactly that. So it is telling me R2, I'm reading R2 and I'm reading the temp1, right? I'm reading the temp1 register and I'm performing addition operation. I already don't have started the addition operation. First operation should be what? First operation is basically fetching the address from the PC. Okay, reading the contents of the PC. That should be the first operation. So I see PC only here. I'm reading the contents of PC from here. So obviously I will start my instruction fetch cycle from here. So this will be the first operation. Reading PC, writing MAR, which is correct, right? I will read from the PC and I will write that value to MAR address because it is an address. Then after that I will read from the memory. I'll go to that memory location, let's say 2000. I'll go to that 2000 location and then I will read that value, and that value will be stored where? That value will be stored in instruction register. So after this I should have instruction register. Yes, instruction register is here. So I read from the memory and then I store it in the memory data register, or like not memory data register. I read from the memory, and then what happens is that value, right? That value from the memory, it is stored in the memory data register. That instruction is stored in the memory data register, and from the memory data register we connect it to the instruction register. Okay, that goes into the instruction register. So obviously second portion will be instruction register. Then what happens is, now I know the instruction. Now it will go to the control unit and it will decode the instruction. So what is the instruction actually? It is R1 plus R2. So what I will do? Then I will store the values of R1 and R2 in some temp1 and in this temp1, right? I store value of in this temp1, and one operand is can directly go into the ALU. So I will do temp. I will write something in temp1. Here I am writing something in temp1. Here I am writing something in temp1. Okay. So temp2. Which one shall I choose? I should choose temp1, right? Because after this what will happen? I will load the values on my temp1 and on the other ALU input that is directly connected. So yeah, R2 read. I will read the R2 and store it in temp1. So it is correct. Okay, just hold on. R2 read. Okay, no, this is not correct. Here, right? I am reading R1 and storing it in temp1, writing in temp1. So this will be the third phase where I will read from the R1 register and then store it in temp1. And the other input I can directly take. I don't need to store in a register. So then what I am doing is I am reading R2 and I am reading temp1. So R2 is directly being read. If R2 is directly being read, it is on the bus, right? So I will read here from the ALU, and temp1 is also directly being read. So R2 and temp1 both are being read, and then I am performing addition operation, which is correct. This R2 and temp1 both are being read, and I am performing addition operation. Then I am storing it in some temp2 register, known as accumulator, right? Writing back the result in temp2 register. This will be the fourth one, and this temp2 R0 write will be the final one, because finally I am storing it in R0. So this will be the fifth one. So which option will be correct here? So I can see first is this one. So 3 is first. First I am starting with 3. Then I am going to 5. Then I am going to 2. then I'm going to 1, and then I'm going to 4. So 3 5, okay, just hold on. Yeah, 3 5 2 1 4. Yeah, option C. So this was supposed to be option C. Option C will be correct. So it's not that difficult. You just have to identify, understand the data path, because I've explained you what exactly happens in data path, right? I've explained. So previously I was I think I have made a mistake here. Here, right? I have told that it directly goes to the instruction register, which is a bit incorrect. If I've told here it directly goes to the instruction register, this is incorrect. Here what happens is it goes to the, that is wrong on my behalf. It depends on architecture, but here generally it goes into the memory data register. Okay, so after it goes to the memory data register, from memory data register, then we store it in the IR. So it was my mistake on behalf. It first goes to memory data register, and from memory data register it goes to the IR. Okay, so let's like this is the solution, right? So there I just made a bit of mistake. So now let's start with the control unit. So what is a control unit? I explained it. Control unit is the brain. It's a component responsible for directing operation by generating control signals. It ensures coordination among all hardware components and enables execution of instruction. So it gives some control signals. It will say that whether I need to give out the data, whether a particular component needs to give out the data or take in the data. Okay, that is what control unit is. It is connected to everything. Okay, it is connected to everything. So what is the function of a control unit? It first of all generates control signals, sends specific signals to components like ALU, memory register to execute operation like data in, data out, perform addition, perform division. It will send the control signals. Synchronize operations, ensures all components work in univision by following the sequence dictated by the instruction cycle. So all like it has to synchronize everything, right? That I get the result at a correct timing. Okay, it's not like I have loaded some value in temp 1 10 cycles back, and now I am performing, after 10 cycles I am performing addition. So temp 1 can store some other value, so I have to synchronize everything. Then obviously it has the task of instruction decoding. What is that instruction? What does it mean? Is it telling me to perform addition operation? Is it telling me to perform division? Or is it telling me to store some data, load some data? That control unit will do. It understands that. So how do we do? Basically, how do we decode? So there is one name known as control variable. Control variable represents the name of the control signal. PC in, ALU out. PC in meaning it is the wire that is going to the in of the PC. So if this signal is 1, if PC in is 1, then PC will understand that it has to take input from the common bus. It will take input from the common bus. If PC in is 1, it means it will take input from the common bus. Okay, and if ALU out is 1, then that means I will ALU will load the data on the bus. If PC in is 1, then PC will load the data from the bus, and this is load the data to the bus. Okay, now what is a control word? A collection of control signals generated simultaneously by CU to perform a specific operation. So a control word is basically collection of control signals. So each bit will represent a particular control variable. Let's say the 0th bit here, right? 0th bit here represents PC in. Okay, I will just reduce the size. 0th bit here represents PC in. First bit here represents PC out. Second bit represents ALU in. Okay, and like that. Each one represents a control variable. And at once I simultaneously send this control signal to the whole bus, so that every component knows what it needs to do, whether it needs to perform write or read operation. So we send it, right? We directly send it on the bus. So this is a control word. And in each CPU cycle, a control word is generated. In every CPU cycle, what is CPU cycle? I will explain that. In every CPU cycle, new control word is generated. Okay, we can think of this like micro operations. micro operations. Previously I haven't explained to you exactly what a micro operation is. This is exactly what a micro operation is. So every time a new micro operation is being generated, that means a new control word is being generated. So control signal gives control word, like a control unit gives control signals that you have to perform a new task. So some data in, some data out will be turned on, right? So this is the actual meaning of micro operations. Okay, so I hope now the concept of micro operations has been cleared. So we will understand the control word more with an help of example. So here I have a control word, okay, and I have 14 components here, just the hypothetical system, and I'm performing the addition R2 plus R3 and storing it in R1. Okay, so I have this many bits here. Okay, so each bit has a designator. So this is a control variable, ALU in. If this particular bit is 1, that means ALU will take input, and if this particular this position is 1, that means ALU will give output. Okay, all of it depends on the control word. This is a control word. Okay, so to perform this, first I have a micro operation, that is fetch the instruction into IR. So it is a micro operation, right? So what we do, we take PC out and take memory in. So we make PC out signal 1 and we make the memory in is not this, right? AR, this AR in to be 1, correct? PC out third bit to be 1 and fourth bit to be 1. Third and fourth. Obviously there will be more micro operations. I'm just saying you the high level stuff. Okay, so this is the first one where I will just mark the points for my better understanding. This is ALU, this is PC, this is address register, this is instruction register or data register. Yeah, this instruction register. Okay, I forgot to write the data register. I hope you understand that data register is also there. Actually, first it goes to the data register, then it goes to the instruction register. Then I have the registers, right? R1, R2 and R3. Just a hypothetical system. Okay, somewhere I may have messed up. Yes, here I have messed up. Here R1 will be here, and this will be R2, and this will be R3. Okay, so currently what I am doing PC out to be 1. So this third position will be 1 and my AR will be 1. Everything else will be 0. Okay, everything else will be simply 0. Just giving you a hypothetical system, don't go into the theoretical here, just I'm trying to explain something. So this is a control word that is generated, that the control unit will send. This will be sent. This is a control word that will be sent on the common bus, and in the next step it has been loaded into the instruction register, right? In the next state it will be loaded into the instruction register. So now what will happen is this MAR PC will be 0 now. MAR out will be 1 and IR will be 1. IR in will be 1, right? It will take the input. And in the next, I'm just giving you a high level example. In the next cycle, what will happen? Now we will decode. Control unit has understood what is the instruction, so it has decoded. So it will take input from R1. This R1 will be R1 out will be 1. Okay, R1 out will be 1 and your ALU in will be 1, right? ALU in will be 1 and R2 will also be it will not be on 1 simultaneously. We will store it in some memory data register, then it will be loaded in the ALU. Okay, this will be 1, this will be 0 only, and your R2 also will be 1 in the next cycle. Okay, it will be stored in some temp register value. I'm not showing that. Okay, I hope you understand. I'm not showing the temp value register. It will be stored somewhere. So first I store the value of R1. Then what I can do, I can directly add, right? I can directly add. So ALU in will be 1. So opcode, all those things are there also. I'm just ignoring that. Okay, ALU has only one operation, that is add. Okay, ALU has only one operation, that is add. So next I will take R2 out will be 1 R1 will be 0. So now what it will do, it will perform the addition operation. It performs the addition operation. ALU has performed the addition operation, and next the result, this is 4, this will go, this time my R2 will be off and my R3 in will be on, right? So it will take the input and ALU out will be on. It will store the result on the R3. Okay, so this is how a control word generates and all the things. So of course there will be a opcode, ALU opcode, there will be opcode. So control word also will consist a opcode here. Okay, this will be the ALU opcode. There will be a provision for ALU opcode. Okay, just I am not showing it here, just to reduce complexity. I am not showing it. There will be opcode and there will be many other things. Many other things will be there. I am not showing it. I am not showing that. I am just trying to explain it. Okay, I'm just trying to explain one particular concept, that how does my control word gets generated. That is my only target to explain. How is my control word getting generated? So I hope you can ignore this ALU opcode for now. There will be a ALU opcode that I am ignoring for now. Okay. That you can ignore. Okay. So this is how a control word gets generated. Let's now understand a new term, that is CPU cycle. So what is a CPU cycle? It is the, like I've told right already, that control unit sends control word and control word represents micro instructions. So the time required to perform each micro instruction is known as the CPU cycle. So that is one cycle, right? One cycle. Now it may so happen, I'm rephrasing it. I'm rephrasing my definition. The time required for the CPU cycle is exactly the time required to perform the each micro instruction, each micro operation. Now CPU has a clock. If you have heard like your CPU, right? Intel is CPU has 1 gigahertz clock, 2 gigahertz clock. I think you have heard, whenever you have gone to the market to buy processors, you have heard about this. What is this? This is unit of frequency. This is unit of frequency, and this is what actually? This is the clock frequency of that particular CPU. Clock frequency. Okay, this is the clock frequency of that particular CPU. Now, is this same as the CPU cycle time or CPU cycle rate? No, this is not the same, because to perform different micro operations, the CPU will take different time, but it will always be a multiple of that this CPU cycle. What do I mean by this? What does it mean? It means clock frequency. What is the unit of frequency? What is the definition of frequency? Frequency definition is cycles per second. And to perform each micro operation, right, it may be required that I have to take 2 cycles of a clock, 2 cycles of a clock, or 1 cycle of a clock. Let me give you an example. In a micro operation, I'm doing some read operation, right? So it will require me 2 cycles. In a micro operation, I will do write operation. It requires me 1 cycle. It is hard coded. It is the architecture. I will be recording 2 cycles to complete a read operation and only 1 cycle to complete the write operation. It is hard coded. Just assume. So if I assume this, now if in an instruction I have both read and write operation, what will be the average number of cycles that I needed to go through? Average, how will I compute average? 2 plus 1 divided by 2, that is 1.5 cycles. So each micro operation, I will write here, each micro operation can take different different number of cycles. Different number of cycles. Okay, each micro operation can take different number of cycles. So what I will do, I will take the average of those and I will compute the average cycles. This is the average cycles. Okay, so now if I have computed the average cycle, there is a term known as cycles per instruction. So this tells me how many cycles on average each micro operation will take. Okay, or like not micro operation exactly, how many cycles each micro instructions will take. This is cycles per instruction, micro instruction. Okay, cycles per instruction. So this is basically, if I combine a lot of micro operations, that gives me micro instructions. Okay, so this will be micro instructions. So this is micro instruction. Okay, so now if I want to compute what is the time taken by the CPU to perform n of these micro instructions, how will I compute that? So I know this, right? I know clock frequency. I know clock frequency. So can I compute how much time does each cycle take? Time taken by each cycle. So CPU cycle time will be what? Time taken by each cycle is basically 1 by clock frequency, right? 1 by clock rate. And if I know the average cycles per instruction, then if I multiply this, I know that this is 1 cycle time. Okay, and if I multiply this with the CPI, what I will get? I will get the instruction time, right? Instruction time. I will get the instruction time. So that will be CPI divided by clock rate. Now let's take, this is just a single instruction. So a single instruction can have many micro operations. So it is a micro instruction. Now if I have a program, so what time it will take me to calculate the whole, like to compile the whole program, right? Or to execute the whole program. It will be, if I have n instructions in that particular program, then it will be n times CPI. Okay, now the CPI, right? If a program, like I am just giving you a lot of thoughts. So first I will just give you an overview. First I have a program, right? Your normal C code. Okay, C code. In C code you have many instructions. Each line is instructions. Okay, instructions. Each line is an instruction. And in instructions, it is a micro operation, because C also, if I write here I equals to 5, it doesn't happen instantaneously. It may take more cycles, right? It may take more micro operations. So in atomic level, I have micro operations. Micro operations. Okay. So this is called, like sometimes this is also called micro instruction. Okay, sometimes this is also called micro instruction. So I am telling you, I like to perform each micro instruction, right? Each micro instruction can take different number of cycles. So there can be I1, I2, I3. So this, to perform this micro instruction, I may need CPI1, I may need CPI2 and CPI3. CPI2 and CPI3. So what will be the, I have to compute the average CPI actually. Because each instruction will take different number of cycles, because it will have many micro instructions. So I was wrong here. I don't directly calculate the average of cycles. Sorry, I was wrong here. That your micro operations will be same only. Micro operations is 1 cycle only. Okay, each micro operation is 1 cycle. So here it is 1 cycle only. I was wrong here. 1 cycle. But micro operations are made from instructions, and instructions can have 3 micro operations, 2 micro operations, or 5 micro operations. So micro operation is related with the clock frequency. Okay, and each instruction will have many micro operations, 5, 4, 6. So what I will do, instruction I1 has 5 macro operations, so its CPI will be 5 cycles. Instruction 2 has 3, instruction 3 has 2. So what will be the CPI average of this whole program? It will be 5 plus 3 plus 2 divided by 3, whatever this value comes out to be, 10 by 3. So average cycles per instruction is 3.33. Now what will be the total time? Total time, although it will not be exactly accurate, but it will be simply the program will contain n of this type of instruction, I equals to 5, then I plus plus n of this number of whatever the number of instructions I have. So I'll multiply n, I'll multiply with CPI average, and I will divide by the clock rate, correct? Because this is the total number of cycles. Although this is not exactly accurate, but that is how we calculate, and this is the time taken in each cycle. So this is what, like I have written the formula only. This top thing is the total number of cycles, and this bottom thing is what? This is the, not this bottom thing actually, this reciprocal, right? This 1 over something. If I have written 1 over here, 1 over this whole thing, okay, this is equals to what? This is the time taken to perform one micro operation. Okay, so if I have n instructions in the program, the execution time of n instructions will be n multiplied by this. Okay, total number of cycles in n instructions. Or what can I say about these cycles? This cycle I can talk also about micro operations, relate with micro operations. Okay, so what does execution time actually depend on? This is not exact formula, this is the average formula. So average is good enough approximation for us. So it is the total, like it depends on the total instructions, how many instructions I have, then average CPI, then also clock time and clock rate. So obviously the higher the clock rate, the execution time will be lower. So that's why we search for which processor has the highest clock rate. 2 gigahertz, we search for 5 gigahertz, 6 gigahertz. Why do we do that? Why do we look for bigger numbers? So this clock, as the clock rate is higher, the execution time of each instruction, T execution, will be lower. So that is why we look for it. So obviously there are few trade-offs as well that we will see. Okay, that we will not understand here. That those are physical trade-offs. Those we will not discuss here. Okay, so here I've given you one example of average CPI. Already have computed it. So how do we calculate the average CPI? Actually, we do not do that simple arithmetic average. We do weighted average. There I have just shown you an example. So how do we do weighted average? So it is the instruction count of type into CPI of type. So if I have ALU and ALU has 400, like ALU has to perform 400 types of instruction, its CPI will be 1. Memory will have 300 instruction, its CPI is 4. Branch, if I have to perform branch, there are 200 branch type instructions in a particular program, and its CPI is 2. So I will multiply individually. So like once we'll solve a question, I will understand. So how to perform the average here? What we do, like there is a program. Okay, there is a program. And that program has 400 ALU instructions. Compiler has calculated it has 400 ALU instructions, and it has been given that each ALU instruction takes CPI, cycles per instruction, as 1. This many cycles. We require only 1 cycle. And for 300 memory instructions I have, like either read or write the data from the memory, my CPI for that particular thing is 4, right? You can observe it is a very costly task. It takes very high number of times, the cycle time for the memory read and write. And I have 300 branch type instruction, and what is it? Its CPI is cycles per instruction is 2. Branching takes 2. So what will be the average? Basically? So CPI average, okay, CPI average will be the sum of the weighted average, right, of each CPI. It will be like, this is the formula. I don't want to tell you the formula. I want to write directly. So I have 400 ALU instructions times its own CPI average. That is 1. So total 400 ALU instructions will take how many cycles? 400. If I have 300 memory instruction, and if each memory instruction takes 4 cycles, to total 300 memory instructions will take how many cycles? 300 into 4. And if I have 300 branch type instructions, and if I have and each branch type instruction takes 2, this is not 300, so this is 200. And if I have 200 branch type instructions and each branch type instruction takes 2 cycles, so it will be 200. Total number of cycles will be 202 divided by the total number of instructions. How many total number of instructions I have? 400 plus 300 plus 200. So this will be 800 plus 1200, that is 2000. 2400 divided by 900. Okay, so if I just calculate it, I don't have the phone, just hold on, I will just quickly calculate it. Two 400 divided by 900, so it is 2.66. okay, I've written this calculate, so it is, yeah, each takes 4, yeah, it will be 2.67. So I hope you understood how to compute the CPI average. Now as I have got the CPI average, what will be the total time taken to execute this particular program? Total time taken to execute the program will simply be equals to CPI average by total number of instructions, whatever number of instructions I have, divided by the clock rate. Because this is how we compute the CPI average. Once we do a few examples, we'll understand this. Okay, now there is another term known as MIPS. What does MIPS means? Means millions of instruction per second. How many million of instruction can the CPU perform per second? Because obviously the CPU can perform a lot of instructions in a single second, right? So it's a better a better stat or a better metric. This is a better metric, right, than normal just instruction per second, because it will be a lot. Every time we have to write 10 into 10 raised to power 10 or something, it will be huge. So this is a better metric. This is a better metric, nothing else. Better metric. Now, if it is how many millions of instructions per second, that means the number of instructions executed in millions divided by total time. That will give me millions of instructions executed per second. So this numerator should be in millions. So it should be number of instruction executed. This is not in millions. I will divide this by 10 raised to power 6. That will give me million, right? Because a million is 10 raised to power 6. So I will divide it by I will divide my number of instructions executed by 10 raised to power 6. That will give me million. The unit will be in million, right? This unit will be million. Okay. So how many number of instructions? I have n. Let's assume n number of instructions. And what is the total time? Total time is, I have already derived, right? Total time is equals to CPI average into n divided by clock rate. CPI average, okay, this is a bit wrong. Yeah, into cycle time. Yeah, so, n into CPI average, 1 by clock rate, right? 1 by clock rate also is known as, or sometimes what do we call 1 by clock rate? 1 by clock rate is also called as the cycle time. Correct? I think I have mentioned this in the previous few slides. 1 by clock rate means how many cycle, what is the period of each cycle. That is 1 by clock rate. Basically 1 by f equals to time period. 1 by frequency is time period. That's it, right? So I can write it like this, I can write it like this, anyhow. Just you can manipulate the formula. So if some data has been given, if you have to find out MIPS, can you do it? Yes, you can, right? You just know the basic thing. Just remember this basic thing, then you can derive the other things. Okay, that is the most important point. So these are few key points that CPI and clock time directly impact execution time. Basically, the lower the period, right, clock period, the higher the CPU will perform. That's why we see Intel has 3 GHz processor. Your new phone, right? New phone has Snapdragon Elite processor. It has higher clock speed. Obviously, it has its drawback. Higher the clock speed, the more heat it will generate, and the more heat it generates, the performance can go down. Okay, it can degrade the performance. So there is a like drawback to it. So that is for other discussion. Okay, so higher MIPS implies better CPU performance, but may not always accurately reflect the CPU efficiency for certain workloads. Efficiency may go down. Average CPI will change depending on the type of the processor, because each processor can have different clock rate, because CPI is dependent on many things. So average CPI also will change upon processor to processor. So this is basically clock. Okay, I hope you know about clock. If you don't know, this is a clock cycle. It just toggles from 1 to 0, and this one whole cycle, for a period when it is 1 and for a half a period it is 0, that is known as a clock cycle, whole time period. Okay, so let's now do few questions from there, like this concept will be cleared better. Consider two processes P1 and P2 executing the same instruction set. So I am executing the same instruction. Okay, so yeah, that is one thing. Assume that under identical conditions for same input, a program running on P2 processor takes 25% less time but incurs 20% more CPI. So if the same program is running on processor P2, it is taking 25% less time. So TP2 is 25% lower than TP1. This is first equation. And what is the other equation? Other equation is but incurs 20% more CPI clock cycle per instruction as compared to program running on P2. So it depends on processor to processor. It is telling me the CPI of P2 is 20% more. So it will be 1.2 of CPI of P1. Now what are they asking me? If the clock frequency of P1 is 1 GHz, so frequency of P1 is 1 GHz. What are they asking? They are asking me the clock frequency, then the clock frequency of P2. What will be the clock frequency of P2? So basic things we know. Even if you tend to forget the results, right? One thing you know, how much time will processor P1 take? What will be the time? How much time does a processor take to completely execute instruction? Total number of instructions. How many total number of instructions? That is n. Let's say I have n instructions and I will multiply this by CPI average. Okay, CPI of that particular processor. Let me name this as TP, divided by the frequency or the clock rate. Okay, or multiplied by the clock period, whichever one you are suitable to remember. So I will write this FP. Okay, so this gives me the total time taken by a processor. So if I just simply take the ratio, right, TP1, TP2, I will get my result, because all these values, like n is same, right? N is same because it is telling me it is executing the same instruction. So number of instructions will be same, but each of them take different times for executing different instructions. So TP1 divided by TP2 will be equals to n will get cancelled simply. So it will be CPI P1 divided by CPI P2 into FP1 divided by FP2. So I know, right? I know the ratio between TP1 and TP2. What is the ratio? It is 0.175. So I need FP1 actually. I have been given FP1. I need FP2. So FP2 is here. So what I will do is I'll move this FP2 on the left hand side. FP2, let me release. FP2 will be equals to TP2 by TP1. TP2 by TP1 is simply 0.75. TP2 by TP1 is 0.75 into CP1 by CP2. CP1 by CP2. CP1 by CP2 is 1.2. Sorry, not 1.2. CP1 by CP2 is uh, 1 by 1 by 1.2, right? So this is what my CP1 by CP2 is, correct? Okay, I think I have made a mistake. Yeah, I have made a mistake. Yeah, because FP1 will be here, right? This will be FP2 by FP1. That is my minor mistake. So actually this will be just swapped. Okay, so it will be 1 by 0.75 into 1.2, and what is FP1? FP1 is 1 gigahertz, correct? So this will become, I can quickly calculate this will become simply this is actually 3 by 4 into 1.2, so this is 0.4, so this will be 1.6 gigahertz. So they have asked, just check the units, what have they asked? They have asked in gigahertz only, so your answer will be 1.6 gigahertz will be the clock frequency of the second processor. So let's do the next question. So next question is again the part 2 of a question that I solved previously. So like all these instructions are there and clock cycles are provided for various operations, and they have asked total number of clock cycles required to execute the whole program. Okay, register to and from memory transfer is 3 clock cycles, add with both operands is 1 clock cycle, and instruction fetch and decode takes 2 clock cycles. Now they like here they missed a point. They should have also mentioned that to instruction fetch and decode 2 clock cycles, this is per word. Okay, they missed this. They should have been given, it should be per word. Instruction fetch and decode per word is 2 clock cycles. If the instruction size is 2 words, then it will be 4 clock cycles. Okay, as the instruction size is higher, it will take more time for me to decode and obviously fetch, right? Because fetch will take more time, because I have to load 2 things in the memory from the system bus, right? Twice I will wait. I have given an analogy as well. If my bus is 8 bits and the register is 16 bits, I will have to do 2 times the data transfer. So they are asking me the total number of clock cycles required to execute the program. So simply for this first instruction, how many clock cycles I will require? To fetch and decode the instruction, I will require, like each word requires 2 clock cycles, and I have 2 words, so it will require 2 times 2, 4 clock cycles. So 2 times 2, 4 clock cycles, plus this instruction itself takes some time, right? That is, it is a move instruction, so it is a register to and from memory transfer, so it will take 3 clock cycles plus 3. Okay, then for this particular instruction, it is also a move instruction, but it is a register instruction, right? Move, register, move, so it only takes 1 clock cycle. Okay, 1 clock cycle, so not 1, so 1 into 2, because each instruction takes 2 clock cycles to fetch and decode, plus its own clock cycle, that is, it is a register transfer, right? It is 3 clock cycle plus 3. Okay, so it will be plus 3. Then I have this add R2 R3. Add R2 R3 means R2 plus R3, R2 plus R3. So I'm adding, okay, I'm doing just this add operation. So to do this add operation, it will take me 1 clock cycle. Okay, they have told me, right, add with both operands in register, so it will not take me any extra clock cycle to load it somewhere. Okay, so 1 plus the to fetch the instruction is 1 times 2, right? Because it is a 1 word instruction, so 1 times 2 plus 1. Then next is this move 6000 R2. Move 6000 R2, so I am moving the contents of R2 to 6000. So obviously again the instruction size is 2 words, so it will be 2 times 2 for the fetch and decode, plus this register transfer takes 3 clock cycle, 3, and hold, right? Hold, remember this, that for hold we only will need to get the fetch, right? We only will take some time to fetch the result. They have not mentioned how many clock cycles I will require for hold to complete, so I will assume 0. So assume for this, right? For this, assume 0. Okay, obviously I have to fetch the instruction, that I have to do, but after fetching, how many clock cycles will be required for this operation, they have not mentioned, so I will assume 0. So this is 0. So to fetch it, it is a 1 word instruction, so it will be 2 times 1 plus 0. So overall what result I will get? This is 4 7, this is 5, this is 3, this is 4 7, this is 2. So 7 7 14, 14 5 19, 22 24. So your answer will be total of 24 clock cycles. Option B will be correct here. Okay, so like I know there are few ambiguity points, so don't stress about this. Currently I hope GATE will provide more information regarding what each instruction takes how much clock cycle, but if they haven't, few things you should know. This is the thing that you should know. Okay, don't take too much stress. Few things you should know. Just by solving questions you will get to know what things you should know and write in your short notes. Okay, so we have learned all this. We have learned about CPI and all those things. Now we will learn a few types of control unit. So first one, we have already learned about it. Okay, indirectly it is called as hardwired control unit. Hardware control unit is what? It is a control logic is implemented using gates, flip-flops, decoders and other digital circuits. Working based on the instruction opcode. CPU generates specific control signals using combination logic. So what happens is, the designer, before the CPU has been designed, right, he decides exactly in the hardware what does each instruction means. Okay, so how to execute a particular program, the designer will decide it, like a specific task like addition, division and all those things. So here what happens is, we have a clock generator. Clock generator is there for like obvious reasons. At each clock some control signal will be sent. Okay, and what will happen, that the designer will decide before manufacture what type of control signals need to be sent for particular instructions. Okay, particular instructions. Okay, so one important portion is this, it is hardwired. So it is a hardware thing, we cannot change it. Anyways, we cannot change control unit, but there are few modality which we will learn in the next lecture about a different type of control unit. Here everything is present in hardware, so we actually implement hardware logic. We don't implement software logic. In the next lecture we learn we will actually implement software logic. What do we mean by hardware logic? Just we make using combination logic, boolean gates and all those things, right? Logic gates. Okay, so what happens is, here we generate a control word. According to each components. We'll see an example there, will understand. Now this is very good. Okay, so this has very good advantage as it is faster due to direct hardware implementation. We directly implement hardware. Okay, it is implemented in the hardware, so it is very faster, can be optimized for specific task. But this has some disadvantages, that's why we don't use it. What is the disadvantages? Difficult to modify once or update once designed. So as we implement it in hardware, it is implemented in the hardware, right? So we cannot modify it. Later on, if you want to modify that, the add operation, the control signal should be something else, I cannot modify it. It is required actually, sometimes modification is required, so I cannot do it. Okay, as it is a hardware thing. Complex wiring makes debugging and reconfiguration challenging. So if we have lower number of instructions, then we will require less number of hardware components, right? I told you previously, there was one example, if I have 36 components, how many wires I will require, I told you previously, right? But control unit will require all the wires. If it is a hardware, control unit will require so many wires and so many logic decoding circuits. So if you have so many elements, then if it is hardware implemented, right, it will be very, very difficult to make that logic decoding circuit, because decoding circuit is hardwired. Once we'll see the next control unit in the next lecture, there we'll understand why am I telling that it is challenging. But this one I hope you understand why it is difficult to modify. It is hard coded, right? It is hardware. So changing hardware is very difficult. How will you go inside the CPU? CPU is so tiny, right? How will you go inside the CPU and change the control unit? No, you cannot. Okay, so that's why. So basically what happens is, generally we have a lookup table. In hardware configuration we have a lookup table, and what happens is, our control unit, right, will send a control signal. how it will send? It will send a control word, right? It will send a control word. Okay, it will send a control word. And let's say, like, I'm just giving you example that this is control signal 0 or like or something, control signal 0, control signal 1, okay, control signal 2, and so on, correct? And for each time cycle, right, each clock cycle, for particular instructions, it is written in the hardware itself that for I1 instruction, let's say this I1 instruction is add. This instruction is add. For I1, it is defined. We defined it that if I am doing some addition operation, the control signal of this particular bit will go high for in the first clock cycle. Then in the next clock cycle, control signal CS5 will go high, CS6 will go high. Okay, we define it for I1 instruction. For I2, let's say subtraction, or let's say some move instruction, right? Load instruction. Fourth bit of the clock signal will go high. That means it will, like, fourth wire of the clock signal CU will go high. Okay, so it is, all of this is defined, and we design a lookup table. So obviously we know, right, we have this table, and from this we can like design a logic, Boolean algebra logic, and from there we can design, implement it in GATS and and gates, not gates, all those things. We can design any logic, right? So with the help of this, first we have a lookup table. First I define, okay, for add operation, control signal 1 bit will go high, and control signal 7th bit will go high. Okay, so I will make that bit high, 1 1. And for subtract operation, 0 signal will go high and 5th signal will go high. So I make a lookup table, then I implement it using Boolean algebra. So if you have studied digital electronics, you will know we have a table, and from there we can implement any expression, Boolean expression, right? And from there we can implement it with the help of gates. So exactly that is how we implement a hardware control unit lookup table. Okay, so this helps. So first the programmer or a designer first makes this lookup table, then he makes a logic. Okay, Boolean expression helps to make the Boolean expression and then that Boolean expression is used to implement using logic gates. I don't have space. That is the most unfortunate thing. Using logic gates. Using logic gates. Okay, so I hope you know how we implement logic gates, all those things. I am not going into that. So let's do a few questions on this. So this hardwired logic thing, right, hardwired control unit, will get more clearer. So here we have a hardwired CPU. I will just zoom in a bit. Hardwired CPU uses 10 control signals, S1 to S10. So I have 10 control signals. So it is not mandatory that I will have 10 control signals only. I can have many more, right? Now, in various time steps from T1 to T5 to implement 4 instructions, I1 to I4 as shown. So I will implement 4 instructions. I have 4 instructions only. Okay. And in first clock period, it has been defined by the designer that signal S1, S3 and S5 will be high. It has been designed for a particular instruction. You can take this as addition, this as move, this as load, anything you want. Okay. So these signals will be high in the first clock period for I1. For I1 in T2, second clock period, these signals will be high. In the third period, these signals will be high, and so on. And for I2, similar, right? But other signals will be high. So it has been designed. Now, what are they telling me? They are telling me which of the following pairs of expressions represent the circuit for generating control signals S5 and S10. Okay. So this is telling me this is just the Boolean expression. That's it. So what are they asking? They are asking for me to design write down the logic, Boolean logic for signal S5 and S10. It is just a digital electronics question. It is not even a computer organization architecture. Okay. So this is just a digital question. Okay. Digital Boolean algebra. Basically, I have to write the Boolean expression. Okay. I have got a table and I have to write the Boolean expression. Can you do it? I will do this first one. And next next one we don't have any question, but I will do this. But mostly questions for hardware logic, right, will come like this. So what you have to do here, I have to see where does my S5 come. So it's very simple. It's a very simple thing. Okay. So I will write S5 will be equals to what? Here, if I observe that I have S5 in instruction I1 for the T1 clock period. For I2, I have S5. For I3, I have S5. For I4, I have S5. So how will I write it? So we write it like this, that it is present in I1, as well as like here how they have written T1 times something, then T3 times I2. Like I1, I3 are in OR, and it is multiplied with T4. So what I will do, I will see each clock period. I will see like this vertical, okay, as they have provided me the expression. If they would have provided me like it is I1 multiplied by T1 or T2, so I would have gone horizontal. Okay, so I will explain that as well. So I will explain, just hold on a second now. So here in the first clock period, I am observing S5 is on for everything. So it is basically for the first clock period, I1 or I2 or I3 or I4, it is always on. It doesn't matter. In the first clock period, it will be always on. If I am at the, so what does this statement say? That I'm ORing everything. I'm ORing everything means I'm ORing all the instructions. That means it is 1. So it becomes simply 1. It becomes simply 1. So if I am at the first clock period, then I am 100% sure that S5 signal will be on, because that's how the designer has made it. Okay, S5 signal is always on for the clock period 1. Okay, so basically it will be T1. Now then I will do OR. Now if I am at the second clock period, clock period, where is my S5 on? Is it on in the first instruction? No. Is it on in the second instruction? No. Is it on in the third instruction? No. Is it on in the fourth? No. So it is 0 simply, because it is never on. Or in the third clock period, I will go and see it's on in the second and the fourth. So I will only choose either I2 or 4. That's why a plus sign, because it is OR. Or if I am at the fourth clock period, then when is my S5 on? S5 is never on. So it will be 0. So from this particular thing, we get our S5 logic. Okay, just hold on. We get our S5 logic as what? S5 logic is T1 or T3 or I2 or I4. And what about S? What are they asking? What else are they asking? They are asking S10. S10 logic. Now again, I will apply the same thing, right? Same thing. If I apply the same thing, S10, if I see S10 is present for T1 period. S10 is never present. So it will be 0 times T1, or for other periods. Here, right, S10 is present in the second and third instruction for T2. So it will be second or third for T2, or in the third clock period, S10 is present in the last, right, only in the instruction I4. Only in the instruction I4. So it will be I4 times T3 plus in the fifth, okay, not fifth, sorry, in the fourth clock period, S10 is present in instruction 1 and 3. I1 or I3 T4. Okay, then in the time period 5, S10 is present in instruction 2 and instruction 4. So it is present in 2 or 4. I2 or I4. Okay, so this is my T5. So what I can write is S10 will be equals to what? S10 will be equals to I2 or I3 T2 or I4 T3. Okay, I can directly write it, right? This is the result only because it is 0. So I2, so I'll check with option like S5 first, T1, T3. So T1 is here, T3 is with I2 and I4. No, this is cancelled, right? This is wrong. This is wrong. Here S5 is T1 and I2, I4, T3. Yeah, T1, I2, I4, T3. So this can be correct. I will mark this here. This can be correct. And here as well, this is also same, right? This also can be correct. Okay, so first I will check the smaller one, then I will go to the larger one. This also can be correct. Okay, so I have to check all three. Obviously, S10 is I1, I3 with T4. I1, I3 with T4 is correct, but it is missing T2, right? T2 is there, T3 is there. So it is missing T2 and T3. So this is gone. Okay, here what have they given me? They have given me I1, I2, I3 with T2. Sorry, not I1, I2, I3, I4 with T2. I2, I3, I4 is not there, right? With T2. I4 is not there. So again, this also has been eliminated. So only option D will be correct. Here if I see I2, I3 with T2, yes, correct. I4 with T3, yes, here I4 with T3, correct. Then I1, I3 with T4, I1, I3 with T4, again correct. I2, I4, I2, I4 with T5, I2, I4 with T5, again correct. So this is correct. Now, they could have like written this expression in different manner as well. Generally, they write this expression like this only. What they could have done, they could have written it in terms of I. This time they have written it in terms of T. In terms of I, can you write it? So in terms of I, how I will write? So I can copy this particular thing. Okay, copy this particular thing. And if I want to write in terms of I, right? So what you could have done is simply, I'll zoom this a bit. That will be easier for us. So here, if I want to write in terms of I, right, in terms of instruction was, so I will go horizontally now. So horizontally, why is S1 present? S1, no, not S1, sorry, S5. S5 is present here and only here. So it will be I1 will be here and it is only T1. Okay, nothing else. This is my S5. Or in I2, where is S5 present? S5 is present in T1 and in T3. So it will be T1 or T3. This will be I2. Now in I3 is S5 present? Yes, I3 S5 is present, correct. So it will be T1 and S5 is not present anywhere else. So it will be T1 into I3 or then if I go to fourth instruction, it is present in T1. Is it present somewhere else? Yes, it is present in T3 as well. So it will be T1 or T3. So this is how you write instruction wise. You can repeat it for the second like instruction as well. Second signal as well, that is S10. Now if we check I1, like T1 is here as well, T1 is here as well, T1 is here as well, T1 is here as well. So T1 is common everywhere. So T1 will become only T1 and all the other expression will be same. You can cross verify. Okay. So yeah, that's it basically for this lecture. I hope you enjoyed the control unit chapter. I tried to give a lot of analogies. There is still one lecture left for control unit. So in the next lecture, we will learn about microprogrammed control unit. So it will be a better version of this hardwired control unit. Thank you for watching and I will see you in the next lecture. Until then, happy learning.